It's crazy, right? Um, and I want to learn about it. I want to learn what happens when you ground something into the earth. And then how come sometimes you can short out if you ground it? You know what I mean? It doesn't make sense. All right, are you guys ready? Alrighty, this one's called Where Does Grounded Electricity Actually Go? Practical Engineering. I like their channel. I watch a lot of this stuff. Go check them out. Give them some love. Let's learn together. Three, two, one,
Imagine
go!
this scenario. You have a diesel-powered generator on a stand that's electrically isolated from the ground. Run a
Okay.
wire from the energized slot of an outlet to an electrode driven into the ground. Don't connect anything to the ground or neutral slots. Now, imagine starting the generator. What happens? Does current
Okay.
flow from the energized wire?
All right. So you have an outlet, right? Neutral stays where it is. Energizer stays goes here. My guess is nothing happens. Nothing whatsoever because the circuit isn't connected. It's not complete. So I don't think anything happens. Let's find out.
Into the ground or not? Your answer depends completely on your mental model of what the Earth represents in an electrical circuit. After all, the idea of a circuit is just an abstraction of some really complicated
Hey,
electromagnetic
Joe.
processes, and that's even more true on the grand scale of the power grid. Grounding is one of the most confusing and misunderstood aspects of the grid, so you can be pardoned for being a little perplexed.
Thank you.
For example, if I run a wire from the positive
Do you not
side of
need
a
anything?
battery into the ground, nothing happens.
Yeah.
But when an energized power line falls from a pole, there's definitely current flowing into the ground then.
Yep.
Cloud to ground lightning strikes move huge electrical currents into or out of the earth. But my little thought experiment of a generator connected to a grounding electrode won't create any current at all.
No.
I'll explain why in a minute. Even on an electrical diagram, ground is just this magical symbol that hangs off the circuit willy-nilly. But connections between an electrical circuit and the ground serve quite a few different and critical purposes. And I have some demonstrations set up in the studio to help explain. I think you're going to look at the power grid in a whole new way after this, but just don't try these experiments at home. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about electrical grounding.
Okay. I will be disappointed in myself because I have spent years studying electricity. I'm communications navigation specialist in the Air Force. My dad was an electrical engineer, so I grew up around that stuff all my life. I have a bunch of licenses and certifications. And if you're telling me you can use ground as a transition system to complete the circuit anytime you want, I'll be shocked. I don't think that's the case they're about to make, but I'm curious. I'm ready to kind of hold on tight to my hat and learn about this. The bacteria will steal it. You're right. Power. Said it all. I like this, guys. All right.
Why do we ground electrical circuits in the first place? Maybe the easiest way to answer that question is to show you what happens when we don't. For as much importance as it gets in the electrical code, it might surprise you that it's not always such a big deal, and in some cases can even be beneficial. After
It's a
all, lots of
life-saving
small
technique, in my
electrical
opinion.
circuits lack a connection to the ground, even if part of the circuit is literally called ground. In that
love it.
case, the term really just refers to a common reference point from which voltages are measured. That's one thing that can be confusing about voltage. It doesn't actually refer to a single wire or trace or location, but the difference in electrical potentials between 2 points. For convention,
So current can travel through the air, guys. Believe it or not, we think of current can travel through the air. I'm gonna let you guys watch this because I don't want to confuse you guys, and I want to try to learn as well. Sorry.
we pick a common reference point, assume it has zero potential to make the mass symbol, and call it ground, even if there's no reference to the actual ground below our feet. On small, low voltage devices like battery powered toys, the difference in potential between components on the circuit board and the actual earth isn't all that important. But that's not true for high voltage systems connected to the grid. Let me show you why.
So if you didn't get that, guys, the big thing is when you actually see a schematic, right? Ground, like let's say you take a look at a schematic of a car, and when you said you grounded, you're grounding to the body of the car. And in that terms, the ground is used to complete the circuit. It's not literally grounding to the ground. The only time that applies, as he just said, is in high voltage. When you're trying to ground yourself against lightning, or when you're running high voltage through two tall towers, grounding might not be a good idea. Yeah, that's the difference. And I just want to make sure you guys to understand. If you're looking at low power schematics, ground is not the same.
This is a diagram of a typical power system on the grid. The coils of a generator are shown on the left. When a magnetic field rotates past these coils, it generates electric
Thanks, Tom.
current on the conductors. And, very
it too.
generally, this is how we get the three-phase AC power that's the backbone of most electrical grids today. Look at nearly any transmission line and you'll see three main conductors that, again, very generally correspond to this diagram. But what you don't see here is a connection to ground. Let me put another diagram underneath where distance is equal to voltage. You can see our three conductors all have the same phase-to-phase voltage, and they have the same phase-to-ground voltage too. Everything is balanced. But in this example, that connection to the ground isn't very strong, resulting just from the electromagnetic fields of the alternating current, called capacitive coupling. But watch what happens during a ground fault. This could be a tree branch knocking down a power line, or a conductor being blown into contact with a steel tower, or any other number of problems that lead to a short between one phase and ground. Now, all of a sudden, that weak coupling force keeping the phase to ground voltages balanced is overpowered,
And
all
short.
the phases experience a voltage shift with respect to the ground. But the phase-to-phase voltages don't change. In fact, a ground fault on an ungrounded power system usually doesn't cause any immediate problems. The motors and transformers and other loads on the system don't really care about the
So it's not a short.
phase to ground voltage because they're hooked up between phases. This is one benefit of an ungrounded power system. In many cases, it can keep working even during a ground fault. But of course, there are some downsides too. In the example I showed,
escape.
the phase to ground voltages of the two unfaulted conductors rise to almost twice what they would be in a balanced condition. Here's why that matters. Higher voltage requires more insulation, which means more cost. Especially on large transmission lines where insulation means literally holding the conductors great distances away from each other and the ground.
All right, guys, if you've ever wondered what these things are, they're raindrop stoppers. And the reason they're so far away from this kind of stuff is when high-powered wires run high power, you don't have to be connected to something else to have quote unquote escape or grounding. What happens is the electromagnetic fields that the high power creates around the wire can actually jump to the tower or to the ground. So that's why the distance between these is so far. You see it? They all about have the same distance. And you don't want to shorten this distance by water running down the wire and then having the electricity actually go up into the ground. Yeah. There's just so much to process here, and I like it. I hope you guys are understanding this.
Those costs can add up quick.
Because you will have so much loss over long distance if that's the case that it won't be profitable anymore. Literally, yeah. And if you touch the tower, you'll get electrified.
Might seem like an esoteric problem for an electrical engineer, but in practice, it just means that ungrounded power systems can be a lot more expensive, a problem anyone can understand. But that's just the start. Look back at our diagram and you can see the faulted phase potential is equal to ground potential. In other words, their difference is zero. There's no voltage, and when you have zero voltage, you also have zero current. No electricity is flowing from the conductor into the ground, or at least not very much is. You still have the capacitive coupling between the unfaulted conductors that allows a little bit of current to flow, but it's not much. And that matters because nearly all the devices that would protect a system from a problem, like a ground fault, need some current to flow. If you know much about wiring in buildings, you might be familiar with the classic example of a toaster with a metal case. It could be any appliance, but let's use a toaster. Under normal conditions, current flows from the live or hot wire through a heating element and into the neutral wire to return to the grid, completing the circuit. But if something comes loose inside the toaster, The live or energized side of your electrical supply could come into contact with that metal case, making it energized too. This could start a fire or, in the worst case, shock someone who touches the case. So many appliances are required to have another conductor attached to the housing, giving the current a parallel low resistance return path.
Yep.
That low resistance means lots of current will flow, triggering a breaker to shut off the circuit.
Yep.
And it's not just the breakers in your house that work this way. Nearly all the protective devices, called relays, that monitor parts of the power grid for problems rely on fault current to tell the difference between normal electrical loads and short circuits. The simplest way to do that is make sure the fault current is much higher than normal loads. In the case of
They're
the
running a lot of
damaged
power to
toaster,
something
that
like that.
fault current flowed through a conductor that's called ground, but is actually just a parallel wire that connects to the neutral in your electrical panel. But in the case of substations and
So the grounding wire in the toaster has less resistance than you will. So when you touch the surface of the toaster, if there's a short in the toaster, your resistance going to the ground is higher, meaning it has a higher time passing through. And if there's a ground wire, electricity likes to go to the least resistance, so the easiest way to ground. So that's how you're safe. One way you can also try to protect yourself, and this is done in like any kind of like laboratories and stuff like that. You are supposed to wear a certain type of shoe, and not only that, you're supposed to stand on a rubber mat that's fairly big and thick. So if you do get current in your system, it doesn't ground, so you're safe. Yep.
transmission lines, the fault current path is the actual ground. Let's look back at the diagram and convert it to a grounded system. If I add a strong bond to the ground at the generator, things don't look much different in the unfaulted condition. But as soon as you add a phase to ground short circuit,
You
the
actually have a
diagram
short.
looks much different. First, the other phases don't experience a shift in their phase to ground potential. But secondly, there's now a path for fault current to flow through the ground back to the source. And that's the answer to the question in the title of the video. Electrical current, in nearly all cases, doesn't flow into the earth, it flows through the earth. The ground is really just another wire.
But what's the resistance then? I mean,
Although not a great one. Let me show you an
well,
example.
that's my question. Yeah, there you go.
I have a narrow acrylic box full of dry sand. I put a copper rod into the sand on
I mean, it's been proven that lightning can actually travel through the ground. People who've been standing next to trees while a tree has been hit by lightning, they have gotten hit by lightning. It's just there's so much loss, so much resistance in the ground that I don't think it's a feasible way of transmitting power.
either side of the box and connected a circuit with a light bulb so that current has to flow across the sand from one electrode to the other. When I turn on the switch, nothing happens.
Yeah, I understand that. There's no continuity. If you add water and salt, there you go.
It turns out the dry sand is a pretty good insulator. In fact, soil
The
and
rubber
rock
flip-flops.
vary widely in how well they conduct electrical current. The
Air match.
resistivity changes with soil type, seasons, weather, temperature, and moisture content. For example, let's try to wet this sand and see if it makes a difference. Still nothing. Even completely saturating the sand with tap water, only a tiny current flows. You can barely see anything in the light bulb, but the
Yeah, that device measures current, guys, and it's just, yeah.
current meter shows 1/10 of an amp now. Soil resistivity also changes with the chemical constituents in the soil, which is why I'm having trouble getting any current to flow through the sand. There just aren't enough electrolytes. Even with a layer of standing water on top of the sand, it doesn't conduct much current at all. If I add just a little bit of salt water to that standing water, immediately you see the resistivity goes down and the light bulb is able to light.
Yeah.
And if I let that salt water soak into the soil, now the sand is able to conduct electricity too. This resistivity of soil to conduct current is pretty important. Earth isn't a great wire, but what it lacks in conductivity, it makes up for in size. You can kind of imagine current flowing from a ground electrode into the surrounding soil as a series of concentric shells, each representing a drop in voltage between the faulted conductor and the ground potential. Each shell has more surface area for current to flow, and so has lower resistance, until eventually there's practically no resistance at all. But up close to the electrode, the shells are spaced tightly together toward a single point or line. That spacing is related to the resistance of the soil, and it can represent a pretty serious safety issue.
I mean, the closer you
Here's a
are
little
to the rock,
demonstration
the
I
more
set
you
up to
get
show how
shocked,
this
yes.
works. This is a length of nichrome wire connected between mains voltage with a few power resistors in between to limit the current. When I flip the switch, electrical current flows through the wire, simulating a ground fault. This length of nichrome wire is resistive to the flow of current just like the soil would be in a ground fault condition. You can see it heat up when I flip the switch. That means the electric potential along this wire is different at every point.
Ooh,
I can
science
show
has
that just by
intentions.
measuring the voltage with a meter at a few different locations.
We're getting
Remember that
educated.
voltage is the difference in potential between 2 points, or in the case of Zap McBodyslam here, between 2 feet. When Zap steps on the wire, his legs are at 2 different electric potentials, and unfortunately, human bodies are better conductors than the ground. That difference in electric potential creates a voltage that drives current up into one leg and down out of the other.
Straight through your
In
heart.
this case, I just have that voltage turning on a little light, but depending on how high that voltage is and how well Zap is insulated from it, this step potential could be a matter of life or death. In fact,
The reason electricity travels mostly through your heart, especially if it's going from one side of your body to the other side of your body, is your veins. Your veins become a circuit. Your veins become a circuit, right? Oh my God. I have been shocked by a aircraft power, which is at 400 hertz, and that thing hurt. I know I didn't fly across the room, but it felt like I flew across the room. I definitely felt like I passed out. It definitely stings for a week. It felt like it anyway. It hurt for like an hour, I want to say. Aircraft power is nothing to mess with. Oh, yeah. IS-21.
power line technicians are often encouraged to hop on 1 foot away from a ground fault to reduce the chance of a step potential.
Are you
It
serious?
sounds silly, but it might save
I
their
want to see a
life.
video of that.
Similarly, power technicians often come into contact with the metal
Bad.
cases around equipment regularly. So, if a ground fault happens on a piece of equipment and the resistance of the grounding system is too high, there can be a voltage between the ground and the metal case, again creating the possibility of a voltage across a person's
Because you're
body,
walking across
called
the ground
touch
that's
potential.
electrified.
The engineers who design power plants, substations, and transmission lines have to consider what touch potentials and step potentials can be
God.
safely withstood by a person and design grounding systems that make sure that they never
numbs
exceed
you,
that
right?
level. For example,
My
most
muscles hurt.
substations are equipped not just with a single grounding electrode, but a grid of buried conductors to minimize resistance in the earth connection. You might also notice that many substations use crushed rock as a ground surface. That's not just because linesmen don't like to mow the grass. It's because crushed rock, like the dry sand in my demo,
Acts as
doesn't
insulator.
conduct electricity well and minimizes the chance of standing water.
Yeah.
But not all power systems use the ground just as a safety measure. There are systems where the earth is actually the primary return path for current to flow. The ground is essentially the neutral line. Electrical distribution systems called single wire earth return, or SWER, are used in a few places around the world to deliver electrical power in rural
I
areas.
did not
Using
know
the earth
about
as a
this.
return path can save costs since
I had no idea about this. They are living off one wire. I had no. Oh my God!
you
I
only
did
have
not
to
know
run
this
a single
existed.
wire. But of course, there are safety and technical challenges too. Similarly, there are some high voltage transmission lines across the world that use direct current, like a battery, instead of AC. We'll save a detailed discussion of these systems for another day because
wanna learn about
there's
this
a
too.
lot of fascinating engineering involved. But I did want to mention them here because many of these lines are equipped with really elaborate grounding systems. Although most high voltage DC transmission lines use 2 conductors, positive and negative, some only use 1, with the return current flowing through the earth or the sea. And even the bipolar lines often include grounding systems so they can use ground return during an outage or an emergency if one pole is out of service. For example, the Pacific DC intertie that carries power from the Pacific Northwest into Los Angeles has elaborate grounding systems at both ends. In Oregon, over 1,000 electrodes are buried in a ring with a circumference of 2 miles or 3.2 kilometers. In California, the grounding system consists of huge electrodes submerged in the Pacific Ocean a few miles off the shore. Unlike AC return currents that generally follow a path that matches the transmission line, DC currents can flow through the entire Earth. In essence, the electrodes are completely decoupled. That does mean they're susceptible to some environmental issues, though. They create magnetic fields that can affect compass readings and magneto-sensitive fish like salmon and eels. In the ocean electrodes, the current can cause electrolysis, breaking down seawater into toxic chemicals like chloroform and bromoform. And stray electrical currents into the ground can flow into pipelines and other buried structures, causing them to corrode. This is also a problem with some electric trains that use the rail as a return path. You may have heard that electricity takes the path of least resistance, but that's not really true. Electricity takes all the paths it can in accordance with their relative conductivity. So even though a big steel rail is a lot more conductive than the Earth, return current from traction motors can and does flow into the ground, sometimes corroding adjacent pipelines and occasionally interfering with buried telecommunication lines too. I've conveniently left out lightning from this discussion.
We're learning right now in the last 10 years that electromagnetic energy from high-powered wires actually does more than we understand. Some people also think it actually can cause harm. I don't know. But we're discovering that it has a huge impact on everything around us. I'm not sure if it's necessarily positive or negative.
Until now. Unlike a conventional circuit where current is always moving, lightning is a type of static electricity.
It's a battery.
It's not flowing until it is.
It's like a capacitor.
And unlike fault current that only uses the ground as a conduit, the current from a lightning strike really does flow into the ground, or most frequently out of the ground and into the atmosphere, restoring an imbalance of charge created by the movement of air or water or something else. We really don't understand lightning that well. But an additional and vital reason we ground electrical systems is so that if lightning strikes, that current has a direct path to the ground. If it didn't, it might arc across gaps or build up charge in the system, creating a fire or damaging equipment. It's not just lightning, ground faults, and circuit return current that flows through the Earth. Lots of other natural mechanisms cause current to flow below our feet, including solar wind, changes in Earth's magnetic field, and more. These are collectively known as telluric currents, and they intermingle below the surface with the currents that we send into the ground. A common question I get about the electrical grid is how to know specifically which power plant serves a city or a building. It's kind of like asking what tree or plant created the oxygen that you breathe. Technically, it's more likely to be one close to you than very far away, but that's not quite how it works. Power gets intermingled on the grid. That's why it's called the grid in the first place. And it just flows along the lines in accordance with differences in potential. And the ground works in a similar way. You can't necessarily draw lines of current flow between sources and loads, lightning strikes, and telluric phenomena. The truth of how current flows in the ground is a little more complicated than that. It all kind of mixes together down there to some extent, but above the surface, it really isn't so complicated. Current doesn't flow to the ground, it flows through the ground and back up. If there is electricity moving into the ground from an energized conductor, go back to the source of that conductor and see what's happening. For the grid, it's probably a transformer or electrical generator, in either case a simple coil of wire. And the electrical current flowing out of the coil has to be equal to the electrical current flowing into it, whether that current is coming from one of the other phases, a neutral line, or an electrode buried in the ground. I hope you've noticed some improvements in practical engineering videos over the past year or two, and that's all due to the help I have making these videos now. Recently, the whole practical...
He's got a whole family, guys. Make sure you guys go give him some support and love. And I like learning from his videos and channels. So his channel name is Practical Engineering. Where does ground electricity actually go? I did not know that. I thought you just dissipated, and I think I'm pretty smart in this. I don't know. I thought I was pretty smart. I thought the God just dissipated. I didn't realize I knew electricity could travel through ground. I didn't realize you can use it as a secondary line to complete a circuit to your house. That's to me is ridiculously crazy, especially the amount of resistance that ground has.